Welcome to the deep dive. Today, we're digging into something really fundamental, something we often just walk over without thinking. Soil water.
Yeah, it's way more complex than just, wet dirt.
Totally. It's this kind of hidden dynamic world, right? And we've got some great material here about how water behaves in soil, so we're going to unpack that. Hopefully reveal some surprising things about the ground beneath us.
Absolutely. Our mission really is to make sense of that water-soil interaction.
Right.
Some of it's pretty complex science, but we'll break it down, make it
Keep it
clear.
engaging.
Right. Think of it as, your shortcut to understanding why water sticks around, how it moves, why it matters so much for plants, everything. No PhD required.
Okay, let's dive in, starting small. The water molecule itself, it's not symmetrical, is it? The sources mention this oxygen and two hydrogens. Kind of lopsided electrically.
That's a good way to put it. Yeah, the oxygen end is a little bit negative, and the hydrogen ends are a bit positive.
Polarity.
Exactly, polarity. And that's the key. It gives water these, well, special properties.
And that leads to these forces the sources talk about. Cohesion and adhesion. What's the difference there?
So cohesion is basically water molecules sticking to each other, like tiny magnets pulling together.
Okay.
And adhesion is water sticking to other things, solid surfaces, like soil particles.
Gotcha.
And these attractions, they're mostly down to something called hydrogen bonding. It creates this whole network. What's really fascinating, actually, is that because water molecules are so attracted to each other, if water touches a soil particle,
Uh-huh.
those nearby water molecules can actually influence other water molecules further away,
Yeah.
ones that aren't even directly touching the particle. It's like a chain reaction of attraction.
You see that all the time, right? Like a water drop hanging on a tap. That's
Yeah.
cohesion holding it together.
And adhesion sticking it to the metal.
Right. And those bugs that skate on water, that's surface tension.
Exactly, surface tension, which is really just cohesion at the surface, making a kind of skin.
Okay, so how does water interact with different types of surfaces then? The sources mention hydrophilic and hydrophobic.
Right, hydrophilic means water-loving.
Mm-hmm.
Think glass water spreads out. Hydrophobic is water-repelling, like wax paper. Or
It's a freshly waxed car, the
Yeah.
water beads right up.
Perfect example. That's hydrophobic. Now imagine these surfaces as tiny tubes, like pores in soil.
Okay.
Because of cohesion and adhesion, the water surface inside these tubes isn't flat, it curves. That's called a meniscus.
Ah, I remember that from school.
Yeah. So in a water-loving hydrophilic tube, adhesion pulls the water up the sides a bit,
Uh-huh.
and then cohesion kind of drags the rest of the water along with it. So you get this dip in the middle, a concave meniscus, and the water actually climbs up the tube. That's capillary rest.
So the soil is basically sipping water upwards through these microscopic straws.
That's a great way to think of it.
And the narrower the straw, the higher it sips. But wait, the sources said something about it being slower in really tiny spaces. Friction.
Exactly right. It's like drinking a thick milkshake through a really thin straw.
Takes more effort.
Yeah. The narrower the pores, the more surface area is touching the water, so more friction. So fine soils like clays with tiny pores, they can lift water higher eventually,
Okay.
but it might take longer for the water to get up there compared to, say, a sandy soil with bigger pores. But in the sand, the water won't rise as high overall.
So it's a trade-off, height versus speed.
Precisely. It's a trade-off.
And this isn't just straight up and down, is it? The diagrams show water moving sideways from a puddle into dry soil or even up a stream bank.
Right. Capillary action works in all directions, where there's dry, attracting soil. It's how water redistributes itself.
Okay, so how is the water actually held in the soil? It's not just sitting in pools, right?
No, definitely not like underground lakes. The sources describe it in, well, three main ways that happen all at once. First, as thin films coating the soil particles themselves.
Like a skin on each grain.
Exactly. Second, filling up the pore spaces between particles, especially the smaller pores.
Uh-huh.
And third, kind of wedged into the sharp little angular corners where particles meet.
So it's really integrated into the soil structure, and when it's wetter, the films are thicker and more pores are full.
You got it. As it dries, the films thin out and water retreats into the tiniest pores in those corners first. They hold on to it the tightest.
Which brings us to soil water potential. That sounds energetic.
It is. It's basically a measure of the energy status of the soil water compared to, like, pure free water at a standard point.
Mm-hmm.
It tells us how tightly the water is held and how easily it can move or be used by plants.
Okay. And the sources break this down into three parts: metric, osmotic, and gravitational potential. Let's start with metric. That's the soil holding onto the water.
Yeah, think of it as the attraction between the water molecules and the surfaces of the soil particles. The soil solids are grabbing the water.
And it's always negative, the sources say. Why negative?
Because that grabbing reduces the water's freedom, its energy, compared to pure water that isn't being held. So it's a reduction in potential energy. The drier the soil gets, the tighter that grip becomes, and the more negative the matrix potential.
Ah, so very negative means plants have to pull really hard.
Exactly. They have to overcome that negative potential, that grip.
Okay, then osmotic potential, that involves salts, also negative.
Yes. If you have stuff dissolved in the water, like salts from fertilizers or minerals, those dissolved ions also attract water molecules.
Uh-huh.
This attraction lowers the water's energy state too, making it less free to move, say, into a plant root. More salt means more negative osmotic potential.
Right. And the last one is gravitational potential. That seems more straightforward. Water higher up has more energy because of gravity.
Correct. Relative to some lower point, water higher up has positive gravitational potential. Gravity wants to pull it down.
So a plant root trying to drink has to fight against the soil's grip, the matrix potential, and the pull of any salts, the osmotic potential.
And potentially gravity if the water is below the root trying to be pulled up. Though usually gravity helps pull water down towards roots, it has to overcome the total potential.
It's like the water needs enough energy to break free. The sources use the analogy of water turning a water wheel, moving from high energy to low energy.
That's the fundamental principle. Water always moves from a state of higher potential energy to lower potential energy. That's what drives all the movement.
Okay, and how does this relate to the water table, that level where the ground is totally soaked?
Good question. Above the water table, in the unsaturated zone, the soil pores have both air and water. Here, matrix potential is dominant and, like we said, negative. And it generally gets more negative the higher you go above the water table.
Further from the free water.
Right. But below the water table, everything's saturated. Here, we talk about hydrostatic potential, or pressure. It's positive pressure due to the weight of the water column above.
So positive pressure pushing down there, negative tension, or pull up here.
Essentially, yes. The total potential below the water table includes that positive pressure. Above, it's dominated by the negative matrix potential.
And the sources briefly mention labs using special membranes to measure these potentials. Seems quite intricate.
It can be. But those measurements help us create things like soil-water potential curves. These are graphs showing the link between water content and matrix potential.
Right, I was looking at those figures. They look really different for sand versus clay.
They really are. What did you notice?
Well, the sandy soil curve drops off really fast. Like it holds a fair bit of water when it's really wet, near zero potential. But as soon as it starts to dry just a little, whoosh, most of the water is gone.
Exactly. Large pores let go of water easily.
But the clay loam curve is much flatter. It holds onto its water much more tightly, even at very negative potentials when it's quite dry. And the organic soil holds a lot across the board.
You've nailed it. It's all about the pore sizes. Sand has mostly large pores, low surface area, weak hold. Clay has tons of tiny pores, huge surface area, strong hold. Organic matter acts like a sponge, lots of medium and small pores. And compaction, you notice. It lowers the amount of water held at wetter potentials, squeezes out the big pores.
Yeah. And then there's that weird thing called hysteresis. The drying curve is different from the wetting curve. Like the soil remembers if it's been wetter or drier.
Huh. That's a good way to put it. It's because pores aren't uniform cylinders. Think of ink bottle shapes or complex networks. When drying, a big pore connected by a narrow neck might empty easily once the neck drains.
Okay.
But when wetting, air can get trapped inside that big pore, preventing it from filling completely until the water potential gets much higher, closer to saturation. So yeah, the path matters.
So the same metric potential, the same tightness, could mean different amounts of water depending on if it's drying or wetting, and especially between different soils.
Absolutely critical point. A sandy soil and a silty soil might feel equally available to a plant at, say, -30 kPa potential. But the silty soil might actually contain significantly more water by volume at that potential than the sand does. The sand just has less capacity to hold it at that tension.
Right. And compaction screws things up too by reducing the total space, especially the air space.
Yes. You can have soil that's quite wet, high water content, but if it's compacted, there might be hardly any air pores left. Roots need oxygen. The sources mentioned needing at least, 10% air porosity?
Yeah, something like that. So too wet can be as bad as too dry if there's no air. Okay, how do we actually measure the stuff in the field or lab?
Well, the most basic way is gravimetric. You take a soil sample, weigh it, bake it bone dry in an oven, weigh it again. The weight difference is the water. Simple, but slow and destructive.
Right. Digging holes everywhere.
Exactly. So for faster, non-destructive readings, we use electronic methods. You've probably heard of TDR, time domain reflectometry.
Vaguely. Sends a pulse.
Yeah, it sends an electromagnetic pulse down metal rods pushed into the soil. The speed of the pulse depends on the water content, because water affects the soil's dielectric permittivity. It's accurate, but can be pricey.
Okay. Any others?
Capacitance probes are common too. They work on a similar principle, measuring how the soil affects an electric field generated by the probe. Often a bit cheaper, maybe easier to use, but sometimes need more careful calibration for specific soils. Making sure those probes have good soil contact is key for both.
And what about measuring the potential, the tension, how tightly it's held?
For that, we often use tensiometers, especially in wetter conditions. It's basically a water-filled tube with a porous ceramic cup on the end that you bury in the soil.
Uh-huh.
As the soil dries, it pulls water out through the porous cup, creating a vacuum, or tension, inside the tube, which you can read on a gauge.
But they don't work when it gets really dry.
Right. They lose suction, the water column breaks. They're usually limited to potentials wetter than about -80 or -90 kPa. For drier soils, we might use electrical resistance blocks.
Like gypsum blocks.
Yeah, those are common. You bury a block made of porous material, like gypsum, with electrodes inside. As the block's moisture changes with the soil's moisture, its electrical resistance changes. You calibrate that resistance reading to estimate the water potential.
Clever. And in the lab?
In the lab, to get those full potential curves, we often use a pressure membrane or pressure plate apparatus. You put a saturated soil sample on a special porous plate inside a pressure chamber.
Okay.
Then you apply air pressure, which forces water out of the soil sample through the plate until the water potential in the soil equals the applied air pressure. You measure the water content at different pressure steps to build a curve.
Got it. Okay, shifting gears now to water movement. What about when the soil is totally soaked? Saturated flow.
Right. Saturated flow or
Like-
percolation. This happens when pretty much all the pores, big and small, are filled with water. Think after heavy rain or irrigation.
What drives it?
Primarily gravity pulling the water downwards. But technically, it's the water potential gradient. In saturated soil, that gradient is mostly due to gravity and any positive pressure head.
And there's a law for this. Darcy's law.
Yep, Darcy's law describes it, and a key term from that is saturated hydraulic conductivity, usually called KSAT.
KSAT. Sounds important.
It is. It's a measure of how easily water flows through a saturated soil. High KSAT means water moves quickly, like in coarse sand. Low KSAT means slow movement, like in dense clay.
The sources had a table. Sand was really high, clay really low. Makes intuitive sense.
Definitely.
Yeah.
And it affects everything from drainage design to how irrigation water spreads. You water a sandy soil, it tends to go straight down fast. Water a clay soil, it moves much slower and might spread out more sideways before it sinks deep.
But it's not always that uniform, is it? Well, water doesn't just seep evenly through every pore. What's this preferential flow?
Yes. Preferential flow is a big deal. It's when water finds shortcuts, faster pathways through the soil, bypassing the main bulk of the soil matrix.
Like what kind of shortcut?
Things like earthworm burrows, old root channels, cracks in clay soils, even gaps between soil aggregates.
So water takes the path of least resistance.
Exactly. And during heavy rain, a lot of water can shoot down these macropores really quickly. This can be a problem for groundwater quality, because pollutants dissolved in the water can get carried down rapidly too, without much chance for the soil to filter them out.
Right, bypassing the filter. And what about finger flow? That sounds weird.
That can happen sometimes, especially in sandy soils that might have some water-repellent spots. Instead of wetting evenly, the water concentrates into these narrow, finger-like paths moving downwards.
Okay, and when the soil isn't saturated, the flow changes again, right? Those big macropores aren't doing much.
Correct. In unsaturated conditions, those large pores are mostly filled with air. Water flow happens mainly through the smaller, interconnected water-filled pores and along the water films on particle surfaces.
And what drives it then, if gravity isn't filling all the pores?
It's primarily driven by the metric potential gradient. Water moves from areas where it's held less tightly, wetter, less negative potential, to areas where it's held more tightly, drier, more negative potential.
So from wetter to drier spots.
Yes. And importantly, as the soil gets drier and the water films get thinner, the pathways for water become much more tortuous and disconnected. So the hydraulic conductivity, the ease of movement drops dramatically, often by orders of magnitude compared to saturated conditions, especially in clay soils.
Much harder for water to move when it's dry. Makes sense. Okay, let's talk about water getting into the soil from the surface. Infiltration.
Right. Infiltration capacity is a potential rate at which soil can absorb water hitting the surface. We can measure it with things like a double ring infiltrometer,
Mhm.
basically cylinders hammered into the ground where you measure how fast water disappears inside.
And that rate changes over time.
Typically, yes. When rain starts on dry soil, infiltration is usually high. But as the surface layers get wet and saturated, the rate slows down and eventually approaches the soil's KSAT, or sometimes even less if surface crusting happens.
And different soils behave differently here, too.
Oh, definitely. Sandy soils usually maintain high infiltration rates. Clays, especially expansive ones, can swell when wet, closing up pores and drastically reducing infiltration over time.
And as the water moves down, it creates that wetting front, the line between wet and dry soil. Not always a neat line, the pictures show.
Now, in real soils, it's often quite uneven because of variations in texture, structure, roots, burrows, all that heterogeneity.
Now, what happens if that wetting front hits a different layer, like fine soil over coarse gravel?
Ah, that's a classic scenario and kind of counterintuitive. You might think water would just rush into the gravel, but often it doesn't initially. The fine soil above has tiny pores that hold water tightly due to strong matric potential, capillary pull. The coarse gravel has large pores with a much weaker capillary pull. So the water tends to build up in the fine layer above the gravel, even moving sideways along the boundary,
Really? It prefers the tighter grip.
until the water pressure in the fine layer builds up enough, gets close enough to saturation to overcome the air entry pressure of the large pores below. Then it will suddenly break through into the coarse layer. This can cause a temporary perched water table in the fine soil above the coarse layer.
Wow. So a layer of gravel doesn't always mean faster drainage right away.
Exactly. And we use this principle. Think of putting greens on golf courses. They often have a sandy layer over gravel. The sand holds some available water for the grass roots above the gravel because of this capillary effect, while excess water eventually drains through.
Clever. The sources even mention using layers to stop drips in nuclear waste sites.
Yeah, designing capillary barriers, using fine layers over coarse layers to prevent downward liquid movement under unsaturated conditions. Pretty critical application.
Amazing stuff. Can water move as vapor too, not just liquid?
Yes, absolutely. Water vapor movement happens in the air-filled pores. It's driven by differences in vapor pressure.
And what causes vapor pressure differences?
Mostly differences in soil wetness. Higher moisture means higher vapor pressure in the pore air. Temperature, warmer air holds more vapor, and also dissolved salts.
Salts again.
Yeah. A salty solution has a lower vapor pressure than pure water at the same temperature. So if you have a spot with lots of fertilizer salts, it can actually draw water vapor towards it from slightly moister, less salty surrounding soil.
Huh. Like the salt is sucking vapor out of the air?
In a way, yes.
Mm.
And this vapor movement, even without liquid water contact, can actually be enough for seeds to take up moisture and germinate.
No way, just from the humidity in the soil air.
If it's high enough, yes. Seeds are pretty good at absorbing water vapor.
Okay, that leads us perfectly into the big one. Plant available water. This is what it's all about for agriculture gardening.
Pretty much. We need some key terms here. Saturation is first all pores full, usually too wet for most plants long term.
Right, no air.
Then after gravity drains the largest pores, usually after a day or two, we reach field capacity. That's often considered the upper limit of easily available water. Lots of water, but still air in the big pores.
The sweet spot, kinda.
Kind of the upper end of the sweet spot, yeah. Then, as plants use water and it evaporates, the soil dries until you hit the wilting coefficient, or permanent wilting point. That's where the soil holds the remaining water so tightly, very negative metric potential, that plants can't extract enough to survive. They wilt and won't recover even if you stop the water loss.
Game over for the plant.
Pretty much. Water held even tighter than that is called hygroscopic water, basically just thin films bound to soil surfaces, totally unavailable. So the available water holding capacity, AWHC, is the amount of water held between field capacity and the wilting point. That's the plant's main reservoir.
But the sources emphasize these aren't sharp lines, right? Like field capacity isn't one exact number.
Exactly. It's a continuum. Water potential changes gradually as water content changes. Field capacity and wilting point are useful reference points, often defined at specific potentials, like Matic 10 or Matic 33 kPa for field capacity, Negative 1500 kPa for wilting point. But they're approximations of a range.
And how do these points change with soil texture?
Big time. Sandy soils have low field capacity and low wilting point. They don't hold much water overall, but what they hold is relatively easy to get out. Clays have high field capacity and high wilting point. They hold a lot of water, but a large chunk of it is held too tightly for plants at the wilting point.
So clay holds more total water, but maybe not much more available water than, say, a loam?
Often true.
Yeah.
Silt loams and loams tend to have the highest available water holding capacity because they have a good mix of pore sizes, holding a good amount at field capacity, but not holding it excessively tight at the wilting point.
Right. And those diagrams showing drought stress patterns linked to soil layers make sense now. Patchy soil means patchy water availability.
Exactly. And organic matter is a hero here. Adding organic matter generally increases water retention at field capacity and increases available water. It improves structure and acts like a sponge.
Good for the soil all around. What about compaction again? How does that affect available water?
Compaction is double trouble. It reduces the large pores, so less water is held at field capacity and less air. It also increases soil strength, making it harder for roots to penetrate and explore the soil volume, especially when the soil gets drier. So it shrinks that available water window from both ends. We sometimes talk about the least limiting water range, the range of water content where soil isn't too wet, poor aeration, too dry, wilting, or too hard, impedes root growth. Compaction narrows that range significantly.
It makes it harder for roots to grow and find what water is there.
Precisely. And root growth itself is often hit hardest by compaction when the soil is drier and stronger.
And obviously, how deep the soil is matters hugely. A shallow soil over rock just can't store much water, no matter the texture.
Absolutely. Soil depth and any root-restricting layers are major factors determining the total water reservoir available to a plant, especially during dry spells.
And plants compete for this water, like trees versus grass.
Big time. Deeper-rooted plants like trees can often access water lower down that shallow-rooted grasses can't reach, especially later in a drought. But dense grass roots can be very effective at sucking up surface moisture quickly.
So you estimate the total available water by looking at each soil layer's depth and its AWHC.
Yep, that's the standard approach. You sum up the available water storage in each horizon down to the rooting depth.
And where are most roots usually?
Generally concentrated near the surface, especially in wetter climates where water and nutrients are abundant in the topsoil. But roots will go deeper if they have to, particularly in drier climates or in soils like sands where surface water doesn't stick around long.
And as plants use water, you see the depletion mainly where the roots are densest.
Right. You can track the drying front moving down the profile following the active root zone. And one last interesting point the sources mentioned. Under severe drought stress, roots can actually shrink.
Shrink. Really?
Yeah, lose turgor and contract slightly. This can actually cause them to lose close contact with the surrounding soil particles, creating tiny gaps that make it even harder to absorb the little water that might still be there.
A final.
Cruel twist of drought.
Wow. Okay, my head is spinning a bit, but in a good way. It is just incredible how much is going on with water in the ground. It's so much more than wet dirt.
It really is. You've got physics, chemistry, biology, all interacting from the molecular scale right up to entire landscapes.
From cohesion and adhesion holding tiny films, to capillary action pulling water up, to how different pore sizes dictate everything, and then how plants have to navigate all that. It's fascinating.
It is. And I think the key takeaway is really understanding that interplay of forces, metric potential, gravity, osmosis, and how soil properties like texture, structure, and organic matter control the whole system. It's fundamental knowledge for agriculture, environmental science, hydrology, engineering, you name it.
Absolutely. And hopefully for you, our listener, this deep dive has peeled back some layers on those unseen processes. Maybe you now have a better feel for why your garden dries out quickly or slowly, how water moves after rain, and just how much work plants do to get a drink.
Yeah, you've got the framework now. So maybe the final thought is, how does this apply to your world? If you're a gardener, how does knowing about field capacity or texture help? If you see erosion or pooling water, what might be happening with infiltration or soil layers?
Or even just appreciating the complexity next time you walk across a field or a park.
Exactly. What other questions pop up for you now about water and the ground beneath us? Maybe the next step is finding out what kind of soil you actually have in your own backyard and how it might be managing water. That could be a whole other deep dive.